also produces some biosolids, and right now they're being sent to the Overgrowth facility to produce a soil amendment product. And they're also interested in finding an alternative disposal method to reduce or divert the amount of waste going to this facility. So, a full-scale anaerobic digester has been proposed to be built at the Glenmore landfill in Kelowna. And to process Kelowna's biosolids, and Sunripe wants to see if they can get in on this. And so our goal was to determine if Sunripe's biosolid waste is a good waste to co-digest with Kelowna's biosolids. To do this, we set up biochemical methane potential assays, they're lab scale batch assays, to collect some preliminary information and model the degradation of the wastes. Each bottle contained the waste, the biosolids, and inoculum, which are microorganisms that digest the waste to produce the methane gas. These are some pictures from the BMP assay setup. Set up 19 different bottles, each with different combinations of the waste. And next, Bruce is going to take you through some of the results from these assays.
Thank you, Chris. I'll just wait a couple seconds for our slide to pop up here with our results. Okay, what you can see here is the results for BMP assays. This graph shows you the cumulative biogas production normalized to the amount of volatile solids removed. You see all of our substrate combinations up there. We monitored for just over 42 days, and as you can see, the production significantly slowed down at around 10 days. This is a very similar graph, except it shows you the cumulative biogas production normalized in terms of substrate added. So this is a very useful graph if you have a known amount of organics you want to add, and you can determine how effectively you can digest your waste. So a quick note about our methane utilization. We estimated that a full-scale digester could produce around 2,100 cubic meters of methane a day. This can be used in a couple of different ways. We can use this directly to heat houses nearby, or we can convert it into electrical energy. And if we do that, we very roughly estimate it could provide the needs of 166 homes. So again, here are some of the benefits of a full-scale anaerobic digester. It would reduce the mass of the waste by about 50%, take away a lot of the odor, and we'd have produced an energy-rich biogas. And it would greatly cut down transportation costs for the parties involved. And as a final benefit, the City of Kelowna could also get carbon credits. So our final results here, we were able to determine that all of our substrates were able to be successfully anaerobic digested and produce biogas, both as single substrates and in co-digestion with one another. And we also found that Kelowna's municipal solids and Sunripe's biosolids would be a very good combination to co-digest with one another, because Kelowna's municipal wastes need to be diluted before entering an anaerobic digester, and Sunripe's thickened waste activated sludge is very high in water, so it could be used to dilute the waste. And it could also provide a lot of valuable nutrients to help the anaerobic digestion process. Thank you very much for listening to our brief presentation. We look forward to the rest of the presenters, what they have to say, and if you have any questions for us, just find us later on. Thank you.
Thanks very much, Chris and Bruce. First out the gate, very brave. So, next up, we've got Jonathan Funk, who is a project engineer with Kerwood Lytle Associates. He provides potable water modeling and planning services to municipal clients, and periodically performs water infrastructure design and construction inspection. So, an interesting little-known fact about Jonathan is that he once invented the extreme sport of rock slide surfing by foolishly tossing big stones down the steep slope he was reclining on.
Thank you for the colorful introduction. So I'm going to be talking about Kingsgate Pump Station, which is a potable water pump station owned by the City of Burnaby, supplying water to Simon Fraser University. What I'm really talking about, though, is renewing critical infrastructure. There's a lot of utility owners or managers here that have to face the question of what do you do when your infrastructure, particularly big, large items like pump stations, that goes right down to individual pipes and valves. What do you do when they wear out? And there's a choice you can make. You can replace or you can rehabilitate. But the problem is, a lot of people don't realize that they have a choice. In a lot of scenarios, replacement seems like a very obvious option. In this case, the Kingsgate pump station pushes water up from the city of Burnaby, or actually from Metro Vancouver source, to Simon Fraser University. It's a very critical pump station because it's the only source of domestic and commercial and fire protection water for the university itself. Being critical, it can have no downtime. And so that makes the question of rehabilitation very challenging. Like, how can we rehabilitate this critical piece of infrastructure without taking it offline? You could build a replacement pump station next door and then switch it over, but you balance the cost of a replacement project against a rehabilitation project. You might find you're not getting the best value for your limited infrastructure budget. So as I mentioned, this is an aging pump station. It's built in the 60s with some equipment that's now getting obsolete. It had a 2400 volt power supply, which isn't very typical in municipal pump stations, and of course provides a very critical service. This is a picture of the existing pump station prior to our upgrades. So in this case, we opted to go with a rehabilitation project. A more challenging construction project, but actually more valuable to the city versus a complete replacement. So now I'm going to talk about a few of the challenges that come along with rehabilitation. It's a bit cautionary, but positive in the end. One example is a brand new bridge crane was required. We couldn't do the upgrades we needed to do with just the existing monorail crane. So we had to take the existing pump station and put a whole new traveling bridge crane in, which of course meant structural modifications to the building itself. And the challenge of installing this in a pump station that's operating while you're working there. So you can't make any mistakes. Things like this will cost a little bit more money to put in a crane versus putting it into a brand new pump station, where you're building everything from the ground up. But you can still realize the savings versus a project where you're building everything from scratch. Similarly, we had a new power supply. So we decommissioned the existing 2400 volt electrical system and motors and put in a brand new 600 volt electrical substation. And we had to operate the two systems simultaneously. So while we had construction crews in there building a new 600 volt system, we also had operators there managing and maintaining the existing 2400 volt system until we could migrate from one to another. And of course, along with the new power supply, we had new electrical panels. We had to put new VFDs in for the replaced motors. And to house all of this, we built a brand new electrical room. So even though we were doing a rehabilitation project, we still couldn't avoid construction altogether. We had, of course, civil and architectural and structural aspects of building a new building. However, if you compare the scope and scale of a new electrical room to the scale of a brand new building where you're doing an entire structure, all the geotechnical, structural, and architectural requirements, we're still realizing a benefit. This is a shot of the foundations for the new electrical room constructed. In addition to the electrical upgrades, we had some very challenging mechanical upgrades to do. We replaced all of the 2400 volt motors with new 600 volt motors. And we had to do this in sequence, one pump at a time, because Simon Fraser University could only sustain a maximum of 2 hours of downtime for Kingsgate Pump Station. So in order to replace a pump, you need to shut things down, take equipment off of one header, put new equipment on, fire it back up again, and then test and commission your new infrastructure. So testing and commissioning required several weeks, or in some cases months, for one pump before you could move on to the next pump. The point is that rehabilitation has some additional complexities that you might not face if you were doing a full replacement project. This is a shot of the finished interior with new 600 volt motors. You can see the new traveling bridge crane on the top, and a few of the other structural changes we had to do just to facilitate a rehabilitation. So what I'm really getting at is there can be some unexpected expenses when it comes to rehabilitating an existing and critical piece of infrastructure. But there can also be some significant savings when you consider rehabilitation versus complete replacement. In our case, a new pump station built next door would have been twice as expensive, offered, let's say, twice the cost for the same value as a rehabilitation project. When facing rehabilitation, we had these specific challenges, these constraints on our construction capabilities. But we still managed to balance the scale in favor of a cost-effective infrastructure upgrade compared to a full project. So The point I want to come across is, in this case, rehabilitation was the way to go. Replacement makes more sense in other examples, I should point out. But make the choice, make an intentional choice. Look at your options. Make sure you're not just assuming we have to replace this, we have to rehabilitate it. Look at both options. Find the option that gives you the best value for your limited infrastructure budget. Thank you.
Thanks very much, Jonathan. Very interesting presentation. We've switched the order a little bit. So up next, we've got Jeremy Close, who is a water resources engineer